Hey students, Mr. Halpern here again. Just realized that I had some crazy hair in the last video, so I do apologize if it looks like my hair is trying to fly away. Um, so last video we were doing some really basic examples going through that stoichiometry roadmap, and we were going basically from grams to grams or from moles to grams of two different substances, known and unknown. So we're just going to continue that here in these problems, sorry. Um, but we're going to try something maybe a little different, right? In this case, we're going to go from grams of water in this particular example, same example as before, but we're going to try to find the volume of oxygen that's needed. So not a whole lot different, but just kind of ending in a different place than moles or grams. We're going to end in volume. So let's try this one. So again, we always start with what is given to us. In this case, 45 grams of H2O. And I've seen some students divide by 1 here. I think that's brilliant. If that kind of helps you to know like what's on top and what's on bottom, that's totally fine. But just know that this is multiplying, so therefore we're going to put grams of water on the bottom because that's dividing, that's the opposite. So we can get rid of it. And we're going to do moles of water. Now, the reason why, let's just backtrack for a second. Maybe I'm already lost you, so I just want to backtrack for a second. I just want to create a little strategy here for this question. To backtrack, we are given grams, but where do we want to go? Where do we want to end up? Well, we want to end up in volume of unknown. So we got to go from mass to moles to moles, and then moles to volumes. So it's really 3 different steps here that we have, right? So we're going to use 3 different steps. Here we go. So the first thing is going from grams to moles. So 1 mole of water is 16 grams of oxygen, 2 grams of hydrogen, so 18 grams. If you don't know that, going to the periodic table, you'll have that on the quiz, no worries. Now we're in moles of water. This step now is going from moles of what we know or what's given to us to moles of the unknown or what we want. So moles of given goes on the bottom. I also know that because if I'm looking at my units, moles of water up here, so moles of water should be down there. So we can cancel them. Now we want to go to what's unknown, which is the volume of oxygen, so O2. So if I'm looking at my previous problem, I notice that it's 3, 2, 2. So we're going to use those coefficients there. So oxygen has a coefficient of 3, and water had a coefficient of 2. All right, that's my ratio. And last but not least, I want to get rid of oxygen moles. I'm going to put that down on the bottom. And that's per 1 mole. But we're going to go to the minimum volume of oxygen. Don't get scared away by the word minimum, right? It's just like if you're making 45 grams of water, then there's an exact amount that you're going to get from this equation, and that just happens to be also the minimum water that you, oxygen that you are needed for making 45 grams of water. You could have more than that. That would be excess, but the minimum amount is what you would calculate right here. So whatever answer is the minimum. All right, so now you're going to have volume. So my volume of a gas is 22.4 liters for every 1 mole. And now we go 45 divided by 18 times 3 divided by 2 times 22.4, and I get 84. Okay, so that is my volume of oxygen gas I would need in order to make 45 grams of water, at least. Okay. If I had less, if I had 83 liters or 82 liters, I'd make less water than that. Now, going on, you'll see some problems where your reaction isn't necessarily given to you. So this is an extra layer of challenge. It's not something that is new. We've done this before, but it's an extra layer of thinking for this question. So let me break it down for you. So what is the mass of copper 1 carbonate needed? So in other words, um, needed to decompose. So we're going to break that down. So that's going to be a reactant here. Okay. If it's needed, then it's going to be, and it's decomposing, it's going to break down. So it's on the left. So copper is here. Now, carbonate, I know what that is, but if you don't know, that's something that might not be as familiar because we don't use it often in class. What you do is you want to go to our periodic table and go to our common ions chart. Okay? And scroll down. It's the second word in the compound, so it's going to be an anion. And carbonate is CO3 minus 2. Okay? CO3, and then this is a charge of minus 2. Okay? Now copper, as it said in this copper is a Roman numeral 1. What this means is it has a +1 charge. Okay? What does this tell you? What this tells you is that if I just had 1 copper and 1 carbonate, I would not have a balance of charges. The carbonate would outweigh, in terms of a negative charge, the 1 copper, which has a positive 1 charge only. So how do I balance this? I balance this by having 2 coppers. And that balances the positive and the negative charges. So now I can remove my charges and I'm good. That is the formula for copper carbonate. Now, it's decomposing and producing copper oxide and CO2. Now, CO2 was given to you as a formula, so, as a written formula. So CO2 won't change, the subscripts there. But copper oxide was not. It was given to you as words. And what you have to be careful of, again, like copper carbonate, is that you're balancing the charges. Okay? So we can assume, again, that this is a Roman numeral 1, so this is +1. But again, we don't know what oxygen is. And if you don't remember, again, going back here is helpful. I noticed that oxygen has a -2 charge. Oh. So if it's a -2 charge and copper has a +1 charge, those are not balanced. To balance them, I would need to have 1 more copper. All right, so that makes it now +2 and -2 total. So now I'm good. I can remove that. Okay, so this is the equation. It's not balanced yet, but the subscripts are correct. Now I need a balance. So let's just double check that it is. I'm looking and I notice that there's 2 coppers, there's 1 carbon, and there are 3 oxygens. So this is already balanced. I'm really happy about this. This is a little bit less work for us, right? So now I start with what's given to me. 1,500 grams of copper 1 oxide. So Cu2O. So now I have to go and figure out, the mass of copper carbonate. So I'm starting with mass. I'm going to end up here. So this is my roadmap. Okay, it's going to be 3 steps. Okay, step number 1, going from mass to moles. So we're going to take this, we're going to divide by the mass, molar mass, of copper to oxide. To figure that out, we're going to copper. Copper is 63.55 grams, and oxygen is 16. So 2 coppers, 63.55 times 2 is 127.1 grams with an oxygen there with 16. So that's going to be 143.1. Okay. All right. So now this is out of 1 mole of copper. All right. Now I have to convert from my moles of what's given to my moles of the unknown. In this case, Cu2CO3. And that's quite simple in this problem because everything is a 1 in coefficients. And last but not least, I'm going to convert to the mass by going 1 mole of Cu2CO3, and we'll take a look at what that is. So copper is 63.55 times 2 would be, what do we say, 127.1 plus 12 from the carbon, which would be 137, 139.1, and then plus 16 times 3 is 48. So that's 139.1 times 48, which would be, oh my goodness, 187.1. Okay. And last but not least, we just solve this problem, and this is 1500 divided by 143.1, and then times 1 divided by 1, and then times 187. 1,961 grams of Cu2CO3. Good. All right. Hopefully that was helpful.